lecture. So today we will be doing in the first part tutorial number 3, which is application on lecture 4 and 5 and 6. So the first question is for this triangular quadrilateral element. So we have this element in figure 1. The shape function n4 for this element is this equation. 1 n4 equal to 1 minus y over b minus x over a squared plus y over 2b squared. So this is the shape function for point 4 here. Okay. We need to show that the n4 function is 1 equal to 1 at node 4 and equal to 0 at all other 5 nodes, which is point 1, 2, 3, 6, 5. So we need to prove that n4 equal to 1 at node 4 and equal to 0 at all the other nodes. Okay, this is the first part of the question. So now I will start sharing the board. So if you can see this one now. So we have question number 1. For question number 1, this is our element. And we have some nodes here. So this is node 4, node number 1, 2, 3, 4, 5, 6. And this is y-axis. This is x-axis. We have here x and the movement w, here y and the movement v. The dimension is a, dimension r, b, b. So this is the shape of the element we have. And the shape function n4 is equal to 1 minus y over b minus x over a squared plus y over 2b squared. This is the shape function. So how can we do this? What we will do is we start like looking at the shape function at y equal to 0, y equal to b, y equal to 2b. This is the 3 level, and we have in level 0, 1, 4, 2, and level B 6 and 5, and level 2B only 0.3. So first of all, at y equal to 0. At y equal to 0, if we put y 0 in this equation, so we have n4 equal to 1 minus 0 minus x over a squared plus 0. So this is n4. So n4 equal to 1 minus x over a whole square. Okay? So if we put n4 equal to 0, so n4 will be 0 when 1 minus x over a whole squared equal to 0. This gives us that x will be at plus or minus a. So as you can see, n4 will be 0 when x equal to plus or minus a and y equal to 0. So if I highlighted this, or just make, so at y0 and x equal to plus or minus a, n4 will be 0. So this means that point 2 and point 1, n4 equal to 0. Now, we want to prove also at node 4 that n4 equal to 1. So n4 equal to 1 if we equalize n4 to 1. So this means that 1 plus minus x over a all squared equal to 1. This gives us that x is 0. So at x is 0 and y equal to 0, n4 is 1. So at node 4, n4 is 1 because node 4, the coordinates is 0 and 0. Node 2, the coordinates are a and 0. Node 1, the coordinates are negative a and 0. Okay? So this is the first level at y equal to 0. The second level is at y equal to b. Same idea, but at y equal to b. At y equal to b, if we substitute here, so n4 will be 1 minus b over b minus x over a all squared plus y over, sorry, we will replace y with b. So b over 2b all squared. So b over b, b over b. So it will be 1 minus 1 minus x over a all squared plus 0.1 over 1 half squared. So 1 omit 1. So we will have n4 equal to negative x over a all squared plus 1 over 4. We want to prove that at this nodes 6 and 5, n4 equal to 0. So n4 equal to 0 in this case when we equate negative xa over a squared plus quarter equal to 0. This gives us that x over a all squared will be quarter, and this gives us that x will be positive or negative a over 2. Okay, if you look at this coordinates, this coordinate is x is positive a over 2 and b. Here negative a over 2 and b. This is the node coordinates. So this means that at 5 and 6, n4 equal to 0. The last level or the last y coordinate we are looking at is at y equal to 2b. If we substitute in the shift function again, if you look back at the shift function and replace y with 2b, this will give us that n4, the shift function at 4, equal to 1 minus 2b over 2b over b, sorry. So 2b over b minus x over a all squared plus 2b over 2b all squared. So this will give us b over b, b omit b. So this will be 1 minus 2 minus x over a all squared plus 1 because 2b will omit 2b, so it will be 1. So we will find that also this one and this one positive will omit negative 2. So we will find that n4 equal to negative x over a all squared. So now to prove that n4 equal to 0 at node 3, So at 0, n4 equal to 0. So this means negative x over a all squared equal to 0. This gives us that x is 0. So if we go back to the element at node 3, as you know, the coordinates are 0 because it is on x-axis and 2b. So n4 at 2b will be 0 only at x equal to 0, which is node 3. So this means that after all of this, we prove that the final is n4 equal to 1 only at node 4 and n4 equal to 0 at node 1, 2, 3, 5, 6. Okay, so this is how to prove that the n4 shape function is only 1 at 4 and 0 all at all other nodes. Okay, now if we go back to this is the first part of question 1. If we go back to the original question, the second part of node 1 is point number B. If we let U3 and V3 and U4 and V4 be only the non-zero degrees of freedom in term, so U3, the movement at point 3 in X and Y, and the movement in at node 4 in X and Y, only the non-zero degrees of freedom. So in terms of these degrees of freedom and X, Y, A, B, what are the element strain, normal strains? Okay, this means that we need to find the normal strains in terms of X and Y and A and B. X and Y are the coordinates or the axis. A and B are the dimension in X and dimension in Y. Another information given to us is the shape function of node 3. So now we know the shape function at node 4. If we highlight this, we know the shape function at node 4 and the shape function at node 3. Okay, so this is the shape function given to us, and we want to find the normal strains for this element. Okay, so if we go back to share, just open a new file. Okay, if we open a new file, for same problem, so question number 1, point number B. What we know is now in 4, the shift function at 4 is 1 minus y over b minus x over a all squared plus y over 2b all squared. In 3 is negative y over b plus y squared over 2b squared. This is the two information given to us. So as you know, if you go back to the lecture, you know that the horizontal deformation will be n3. The horizontal deformation at point 3 plus n4 times the horizontal deformation at node 4. So this is u for the plate equal to n3, the shift function, times the node displacement at 3, the shift function at 4 times the node displacement at 4. For the vertical displacement of the plate, v equal to n3 v3 plus n4 v4. So this is the two equation to find the displacement of the plate or of the element given. Element deformation. Okay, those are nodal displacement. Okay, so now to find the strain, if we go back to the lecture, the strain epsilon x equal to partial n3 dx u3 plus partial n4 dx u4. So the strain, the normal strain in x is the partial differentiation of the horizontal plane, horizontal deformation according to x. This is the first one. So if we substitute here, if we apply the partial differentiation here to n3 and to n4, so epsilon x will be, so partial n3 according to x. n3 is in y, in terms of y, so this will be 0 plus 0. So for partial n3 according to x, it will be 0 plus 0 because n3 is a function of x, not y. Plus partial n4 according to x. So partial n4 according to x, if we go to n4, so it will be 0 minus 0 minus 2x over a squared plus 0. Because this is n4 on top, it is only function in x of this term. This term is the only term function in x. Okay, so now if we like clean this one, so epsilon x will be negative 2x over a squared. So this is the requirement, the strain in terms of x and a. The second part is the strain in y, the normal strain y direction. So it will be again partial n3, but in according to y, v3 plus partial n4 dy v4. So if we do the same, epsilon y, which is partial n3, if we go to n3 at the top, so n3 is a function in y. So we will differentiate the first term, so it will be negative 1 over b, right? Where is n3? This is n3. No, sorry. I forget to put 2 here. So if we differentiate n3 over y, so it will be negative 1 over 2b plus 2y over 2b squared. So if we go up again, sorry. So this one will be negative 1 over 2b. This one it will be 2y over 2b. Okay. So this is the first one times v3. Sorry, here just to forget something here. Here I forget to put u3 and here u4. So this one will be epsilon x 2x over a squared times u4. Okay, so here as well, we will differentiate the second part of the equation. So it will be partial n4 over y v4. So if we go to n4 at the top, so 1 is a constant, so it will be 0. The second one will be negative 1 over b. The third one is in terms of x, so it will be 0. The last one will be 2y over 4b squared, because if you just distribute the square over the two terms, so it will be y squared over 4b. So if we want to differentiate this one, it will be differentiation will be 2b over 4b squared. So if we go down here, so it will be negative 1 over b plus 2y over 4b squared multiplied by v4. Okay, so if we want to finalize this one, just 2 with 4, we will have only 2. So the final epsilon y will be negative 1 over 2b plus 2 with 2 y over b squared v3 plus negative 1 over b plus y over 2b squared v4. This is the final normal strain. So this is the normal strain in x, epsilon x. This is the normal strain in y, epsilon y. Okay. Do you have any problem with question 1? So that's it for question 1. If we go to back to question number 2, question number 2 is easier one. So for question number 2, he gave us three elements, 3 types of element. Just a second. Okay, for question number 2, we have 3 elements and we want to just specify the size of the element stiffness matrix. How can we specify the element stiffness matrix here? We will look at the element type. So this element is 4 nodes, quadrilateral plane strain element. And we know how much is the degrees of freedom at each node, and then multiply the number of degrees of freedom at each node times the number of nodes. Okay, this is how to solve this question. So I will again share my board screen. So now for question number 2, we want to know the size of element stiffness matrix. For question point A, we have quadrilateral plane strain element. So this is our element. How many nodes we have? Number of nodes is equal to 4. Degrees of freedom at each node, how much? How many degrees of freedom at each node for a plane strain element? Each node has 2 degrees of freedom. If you go back to the lecture for a plane strain element, you will find that the number of degrees of freedom at each node is 2. So how much the size? The size will be number of node times degrees of freedom at each node. This is how much is the size. So it will be 8. So this element will be 8 by 8. Okay, because the total number of degrees of freedom will be 8. So now do same at for the second one, point number B. The second element is quadrilateral or quadratic, sorry, triangular, plane stress element. So it is a plane stress element. So number of nodes, 3. And degrees of freedom at each node equal to 4. So the total number of degrees of freedom will be 12. So the size will be 12 by 12. Okay. The third element is quadrilateral, quadrilateral thin membrane element. Okay. This is also for nodes. So how many nodes we have? Number of nodes is 4. How many degrees of freedom at each node? 5. So the total number of degrees of freedom 20. So this element will be 20 by 20. Okay. This is how to find the size of element matrix using the number of nodes and the degrees of freedom at each node. Okay. So this is question number 2. And now we want to go to question number 3. If we go to question number 3, we'll jump to question number 4 and then leave question number 3 after question number 4. So for question number 4, there's still also a text question. So we need to know what is the benefit of using a quadrilateral plane stress element instead of triangular element. Do you know what is the benefit of quadrilateral element instead of triangular element? So quadrilateral plane stress element instead of triangular element. So if we share the screen here, we'll answer this 3 question. So for question number 4, the first point is we need to know a benefit of using a quadrilateral plane stress element over a triangular element. So the benefit is, or the advantage of using a quadrilateral element over a triangular element is that in quadrilateral element, epsilon x, the normal strain, varies according to y. So this means that the normal strains varied with the depth of the cross section for a quadrilateral element. But epsilon x equal to constant, or where epsilon x is equal to constant for a triangular element. So for quadrilateral element, the normal strain vary with the depth, which is more logical for us and for our calculation. So that's why the quadrilateral is better than the triangular element. Okay. So now point number two, the question is, what is the disadvantage of using a quadrilateral element? So a disadvantage, the opposite of question one. A disadvantage of using a quadrilateral element. So the disadvantage is when predicting the shear strain or shear stress for a pure bending problem. So the disadvantage of quadrilateral element when predicting the shear strain, because it is inaccurate. Okay, so this is a disadvantage of using the quadrilateral plane stress element. The third point is, for what type of structure is plane strain used? Plane strain element used. When to use the plane strain element? The plane strain element is used for structures that are very long in one direction. Let's say the Z direction compared to the other direction. Like a dam, if we have a dam like this, so it is very long if this X, Y, and Z. So this is the dam. It is very long in Z, but the other dimension are small. So for example, dams or retaining wall and so on. So this is when to use the plane strain element. The last point or the last question is, for what type of structure is plate or shell element used? When to use the plate shell element? This one will be used for structures where the thickness is very small compared to other dimensions, and the structures are subjected to normal loads. Just and the structures are subjected to loads normal to their surfaces. If we can draw this, it will be something like, okay. So it has two conditions: the load normal to the surface, and also the thickness very small. Okay. This is when to use the plate shell element. Do you have question for this part? Do you have any question in this part? Okay. Now, if we go back to the screen, the questions, this one. So this our final question in tutorial 3. Okay, for this part or for this question, we have a uniform beam modeled by Q4 elements. So we have a model as in figure 2, Q4 element, so quadrilateral 4 nodes element. We need to qualitatively, without calculation, plot sigma x and the tau xy, so the normal stress in x and the shear stress in xy along the top edge of the beam from point A to C. So from A to C. So A, B, C here, as predicted by the elements. Also plot the exact stresses according to the beam theory. Consider the following loadings. So we have two cases. Case 1, F1, which is the vertical load here, is 0, and F2 equal to F3. Okay? The second one is F1 equal to 0, but F2 is the reverse direction of 3. So what F10 means? F10 means that we don't have shear because the vertical load is 0, so we don't have any shear on this beam. This is uh, what we need to understand from this part. So from the first condition, we need to know that the stresses, the shear stresses should be 0 because no vertical force. What is the meaning by the direction of F2 equal to F3? F2 and F3 in same direction? This means that there is no bending moment on this beam, but there will be only normal stresses. So we will have normal stresses. It will be tension. As you can see, if F3 and F2 going out of the beam, this means that both of them cause tension and no bending moment because they are in same direction. But for case 2, F2 negative F3, this means that F3 is going out, so F2 will be going in. This means that these two forces will cause moment on the beam. So the normal stress in case 2 will be due to bending moment. The normal stress in case 1 will be due to the axial force. Okay? So if we start solving this problem, we will share the screen. So now we are question number 3. So we have two cases. I will start with case A, F1 equal to 0 and F2 equal F3. So this is our beam, consists of two quadrilateral elements, Q4. This is what is given in the problem. This is F1 equal to 0. This is F2, F3, and this is F2. So we have two supports here as well. One is roller and one is hinge. The dimension here is 2C. The dimension here is 2L, L and L. Okay. From the drawing, this is x-axis and this is y-axis. This is point A, B, C. Okay. So for the first part, F1 equal to 0, F2 equal to F3. This no bending moment or shear. This is what we understand from here because F1 equal to 0, so no shear. F2 equal to F3, this means we can model this as a tension member here like this. So if we simplify it, it will be something like this. Just for simplification. Okay, so it is no bending moment or no shear, so it is not a pure bending problem or not a beam prob, like a bending problem. So it will be, this problem is beam only element and has degrees of freedom only in x direction. So if we consider degrees of freedom at the nodes, we will have only degrees of freedom in x direction because this is the only direction the nodes will move. So if we give them names UA, UB, and so on. Okay, this is what we understand from the given example, given problem. So if we go to our lectures back, so for this type of element, the deformation U, the horizontal deformation U, is equal to beta 1 plus beta 2 x. So if we want to get the normal strain, epsilon x is the partial differentiation of u over x, as you know. So it will be beta 2. So this is the normal strain, epsilon x equal to beta 2. Beta 2, as you know, is a constant. So we can mention that epsilon x is dependent, don't rely or depend on x. So this is dependent of x, which means that epsilon x is constant. Okay. And because there is no shear. So gamma xy, the shear strain, equal to 0. This will lead us to the shear stress also is 0. So from these two information, we know that how much sigma x, which is constant, and how much tau x, y, 0. Okay. If we want to draw this, because it was required to draw this on the this it was required to plot sigma x and tau xy along the top edge of the beam. Okay, so if this our element is just indication, so this C, this is F3, and this is F2. So if we want to draw indication, so this is as a graph. So we will plot the stress here, and here is the distance x, and this is our 0. So as you know, tau is 0. Tau xy is 0. So this is tau, and normal stress is a constant. So it has a value, but we don't have any values to put. So this is sigma x, and this is tau xy. Okay. In this case, because it is a beam only element, so the exact solution will be similar to the finite element solution. So we can mention that this sigma x will be from finite element and exact. Because this type of elements, the quadrilateral Q4 element, doesn't have problem with the uh, beam only type, but it has problem only with the pure bending problem. So there is no problem with this type of question. So tau xy also from finite element and exact solution will be 0. So this means that the exact solution and finite element solution are similar. Okay, so this is the first case when F2 equal to F3 and F1 equal to 0. So this is the first step. So second part, Q number 3, point number B. The difference is this is given to us in this point F1 equal to 0, so no shear again, but F2 equal to negative F3. This is the main difference here. And again, this is our problem. I will draw it again. We have those nodes A, B, C. Here, F1 is 0 again, but here is F3. This will be F2. As you can see, F2 and F3 are not same direction, so this will cause moment on the beam, like this. So due to F1, F2, and F3, we will have bending moment. So from here, no shear, and from here, we have bending moment. So this problem is a pure bending element or a pure bending problem. So for the pure bending problem, as you know, or if we go back to the lecture, we have three type of strains: normal strain in X, normal strain in Y, shear strain in XY. So normal strain in X will be beta 2 plus beta 4 Y. Normal strain in Y is beta 7 sorry, just a second. Okay, beta 7 plus beta 8 in X, and for gamma XY, beta 3 plus beta 6 plus beta 4 times X plus beta 8 times Y. So this is the three type of strains we have in this type of element Q4: normal strain in X, normal strain in Y, shear strain. Okay, what is the problem here? If we return back to the lectures, we know that we have a problem with Q4 in quadrilateral element, sorry, in pure bending moment. So we have problem of Q4 in pure bending problem. What is this problem is, if we look at the normal beam, this is our beam, the exact solution. So if we have M and M, what is the deformed shape after the moment applied? It will be something like this. And this is theta 1, and this is the correct deformation or the exact deformation. So as you can see, the top edge will have a curvature, the bottom edge will have a curvature, and the angles should stay normal. But for quadrilateral element, the Q4 element, if we have moment M2, so what is the shape of the deformed shape? What is the shape after curvature? The top edge will stay same, so will not change, and the bottom edge will also stay same. So now can you see the difference? So this is our quadrilateral Q4 element. So this is theta 2, and this is the deformation of Q4 in finite element. So can you see the difference? In the quadrilateral element, the top edge and the bottom edge are stay straight, no curvature. And also the angles become not normal angle. So this is this is not correct or not exact solution. So that's why inaccurate. This inaccurate solution from the finite element. Okay, so we can summarize this as at the top beam, at the top edge of the beam, because we are looking at the top edge of the beam, sigma x should be a constant. However, the displacement v is linear in x. So all sides of Q4 element deform as a straight line. And this is the problem. So we can't rely on the element that all the edges are straight lines, because actually in the exact solution or the correct deformation, it is a curve. Okay, so and also another problem is the right angles in, let's say, this figure 1 are not preserved in the finite element solution under pure bending. So this problem only will appear in the pure bending problem. Okay. Another problem is also the shear strain appears everywhere in the element except for y-axis, because on y-axis y equal to x equal to 0. Okay, so what is the problem? What caused this problem? The cause of this problem of shear, because beta 4 doesn't equal to 0. So if we go back to the first three equation we have here, so this is the problem, beta 4. So because beta 4 doesn't equal to 0, this will cause that the shear strain will has a value, which is not realistic, because we mentioned that should be no shear because F1 equal to 0. So the main problem for the quadrilateral for the Q4 element is beta 4 doesn't equal to 0, and this causes shear strain. And actually, the exact solution, there is no shear. Okay, so this is the answer of this type of question, but the last step or the last part of this is to draw the or plot the values of sigma x and tau xy as the previous example. And as you can expect, the shear and the normal strain or the shear and normal stresses on this element is not similar in exact and finite element solution. So if I draw here, this is the element, this is point B, C, sorry. We have F3 at C and F2 here. F1 is equal to 0. If we try to draw here, so we have X and Y and stress. So this is 0. For the shear strain, for the normal strain, for the normal stress, sorry, this is the normal stress. It has a constant value at the top edge. We are only drawing the top edge, so this is sigma x finite element. But there will be small difference between the finite element solution and the exact solution. So the purple one is sigma x for exact solution. Because of beta 4. So this difference is because of beta 4 doesn't equal to 0. So the value of beta 4 cause some difference in the results. Another thing is the exact solution, as you know from previous example, there is no shear for this pure bending beam. So the exact solution is tau xy exact should be 0. But the problem is for finite element solution, it is not 0. It is something like this. So if this node A, this node B, this node C, so the orange line is tau xy due to finite element. What is the cause of this shape, or what is the cause of the difference between the exact solution and the finite element solution? Beta 4 is not equal to 0. So this is the main problem in the quadrilateral 4 element, Q4 element, that beta 4 doesn't equal to 0. Okay. Do you have any problem or any question about tutorial 3? This is all the question we have in tutorial 3, and we will have a small break, let's say 10 to 15 minutes, and then we come back. Okay? Okay, see you after 10 to 15 minutes. So today the second part of our lecture will be the second order and buckling analysis of steel structure. As you know, we have two like different type of analysis, like linear analysis and non-linear analysis and second order analysis, buckling analysis. So we will talk about this now. So at the beginning here, what is the difference between second and first order analysis? The first order analysis assesses the equilibrium in the undeformed shape of the structure. So the first order analysis assesses the equilibrium of the structure at its original position before deformation. While the geometry or nonlinear geometry or nonlinear analysis assesses the equilibrium of the structure in the deformed shape. So this is the main difference undeformed shape and deformed shape. As this deformed position is initially unknown, second order analysis is iterative process because we don't know what is the the deformed shape of the structure, so we need to make some iteration to reach the final solution. Okay, so the second order analysis is iterative solution or iterative method that keep hunting for the final deformed position until a prescribed level of accuracy achieved. So until we reach the accuracy required, so this iteration keep going until we reach the accuracy required. Okay. The second order effects are only significant under the following circumstances. So the second order effects are not significant in all cases. The main cases where the second order effects are significant are where one or more members in the structure is carrying compression load. So the compression load will make the second order analysis important because this will cause buckling or excessive deformation, so need to capture the second order effect. The second is where the structure is relatively flexible so that the deformed shape is significant different from the undeformed shape. So the second condition is when the structure is flexible, so the deformation will be big, so the second order effect will be significant. Just main two cases. Introduction. So we'll have some. This will be also like explanation of the Australian standard part of second order analysis. So it is not only finite element or software lecture, but it also explanation of how to do the second order analysis in the Australian standard. I think you have this file in your in on the system. It is a part of the Australian standard. I will share it with you. Can you see it? Okay. So this file is a part of the Australian standard 400 for 4100, talking about the elastic analysis, what is the assumption, and how to take the second order effects. And here also is explanation of the first order analysis and the method of moment amplification. Okay, so we will talk about all of this now, and I think you have this file on the website on the website, so you can download it and use it. Okay. Okay, so if we go back to our lecture, so this introduction about design of cell structure according to AS 4100 and the standard recommend to use nonlinear analysis result. In the standard clause 4.4 suggests that the design shall be based on second order analysis or first order analysis with moment amplification. So we have two methods, either using second order analysis or first order analysis, but with a moment amplification factor, which means like increase the moment due to the second order effect. Okay. The following example is intended to show how nonlinear analysis may be performed for a simple structure with and without the aid of computer. So this example is a beam. Will show what is the significance of using the second order analysis. As you can see, this assembled beam has a uniform load, which is the self weight, and normal force 30 kilonewtons. The section or the cross section of steel is grade C30 350. The section is 101.6 times 3.2 CHS, circular hollow section. The on weight of this beam is 7.7 kilogram per meter, but for the load combination, we multiply it by 1.2 and we convert it to kilonewton meter by multiply it by 9.8 over 1000. So the final self weight is 0.091 kilonewton per meter. The uniform load is, sorry, the normal force is 30 kilonewton. The span is 7000. So for the first order moment and deflection as normal calculation we do all the time, it will be, the moment will be W times L squared over 8, which is 0.557 kilonewton meter. Okay, we use the subscript M that signifies that this is a linear analysis moment. So M means linear analysis moment. Stars means the applied moment or the moment from the external loads. So this is the moment from the external loads. The second part is how to calculate the deflection or the deformation at mid-span for this beam. You know the basic formula for deflection is 5 over 384 times W star L to the power 4 divided by EI. So it will be 5 over 384 times 0.091 times 7000, because all the dimensions should be in millimeter. 7000 to the power 4 divided by 200 times 10 to the power 3. This is Young modulus of steel. And I from the capacity tables is 1.2 times 10 to the power 6. So the maximum deflection of this beam will be 11.85 millimeter at midspan. Okay. Now, if we consider determining the maximum moment occurring at the center of the beam, but we will do this for only a part of the beam just to see the effect of the second order analysis. So we will take half of the beam, like you see this circle. This is free body diagram number 1. So we will take this half out and study this part. So if we take this part out, so we will have reaction as 0.319 kilonewton, and the load in this area only is 0.319 because we take only half. The moment here is M and the normal is N and the shear is V. So this is a string action at the middle. And this is the horizontal reaction Rx equal to 30 kilonewton. Okay, if we consider determining the maximum moment occurring at the center of this beam, so M, we are looking for M. So to do this, we cut through the beam as we mentioned. So after we cut, to take this to get this moment or get the straining action at this point, let's say this point A. Here is point A. Okay. So if we are at point A here, so what is the moment and normal and shear at A? To get the normal at A, summation Fx equal to 0. So N still negative 30 kilonewton. Summation Fy equal to 0. So we have the load going down, the reaction going up, and the shear force V here. So V is 0. So V at A is 0. The last thing, the last component we are looking at is the moment. Summation MO equal to 0 or MA, make it MA, or let's see, let's rename this and make it O instead of A. So if we have point O here, so if we take summation MO here, so the moment here will be this force times times 1.75 meter, this force times 3.5 meter, and the moment. So we have 0.319 times 1.75 minus the reaction 0.319 times 3.5 plus the moment. So the moment at middle span or at section O is 558 kilonewton meter. Okay. Now, so this was before the deformation. So this is the undeformed shape. After the deformation, how much was the deformation? 11.85. So now the position or the deformed position of the beam is the curve. The reaction is still the same. The applied load is still the same. The span is still the same. So we need here to calculate again V and normal, shear and moment and normal force. Summation Fx equal to 0, N is still 30 kilonewton. Just can you just edit this one in your calculation? This is just a typo here. So it is should be 0.319. So this one is 3.19 and also this one is 3.19. Sorry, 0.319. Okay, because this is the applied load and the reaction. So 3.19 minus 0.3, sorry, 0.319 minus 0.319 plus V, the shear. So the shear is 0 as well. So here we have normal is 30 kilonewton, shear is 0. And what is the next step? The moment. If we calculate the moment now, what is the moment at O now? Or at O now here? What is the moment at O? It will be the reaction, the force here times 1.75 minus the reaction times 3.5 minus 30 kilonewton times the deformation. Because now the point of calculation is far from the center because it deformed. So we have this distance now between the normal force and the point. So we have a distance of 11.85, which is the deflection. So this value was added to the calculation, negative 30 times 0.01185, which is the deflection, plus the moment, equal to 0. Now the final moment is changed to 0.914. So before adding the deflection or when we study the undeformed shape, it was 0.558. Now after adding the deformation or studying the deformed shape, it become 0.914. Okay, can you see the difference? So now, if we look at this values, we see that the second estimate of the maximum bending moment, which assesses the equilibrium at the deflected position, is 64% larger than the simple first order moment. So if you calculate the difference between 0.914 and 0.558, you will find that the estimation in the second order analysis is about 64% larger than the simple first order moment. This is clearly a significant difference, which demonstrates that for the structure, it is not adequate to use the first order moment for design. So this values show that the second order analysis is significant when we design the steel structure. The second moment calculated is also incorrect because it takes the account of the first order deflection, which was smaller than the real deflection. This is another problem we have, that the deflection we use here, the 11.85 is not the real deflection because we use it from the first order analysis. Okay, so it is not very accurate, but it is better than the first order analysis. Okay, now if we jump to this example, So this is like a beam analyzed by space gas software. There's a different software. So this beam is under a normal force and try to like measure the moment and deflection at different values of normal force using space gas. And we in space gas there is also option of nonlinear buckling analysis. So these results are for nonlinear buckling analysis using space gas. As you know, we have a theoretical value of buckling, which is called Euler load or Euler critical buckling load. This value is pi square EI over L effective square. Okay. NOMB means the critical buckling load, but this is the abbreviation from the Australian standard. So the Australian standard gives the buckling load a name of NOMB. Okay, so if we calculate the NOMB or the buckling load of this beam, it is pi square times EI. E is 200 times 10 to the power 3 times 1.2 times 10 to the power 6 divided by 7,000 square. So the buckling load for this beam is for 48.3 kilonewton. Okay, so it is similar to this one, but we just want to calculate how much is the buckling load. So the buckling load or the critical buckling load is 48.3 kilonewton. When we try different loads on the space gas, this was the moment when n equal to 0. So the first line is when n equal to 0, the moment was 0.58. This means that the moment is from on weight only. The second one is for n equal to 10 was 0.73 kilonewton meter. The third one, when it's 20, was 1 kilonewton meter. The fourth one was 1.56 kilonewton meter when the normal was 30 kilonewton. So this is the case in our example. The moment was 0.56 meter. Okay. When n star equal to 40, the moment was 3.44 kilonewton meter. You see how much is the difference? How much is the moment increase when increasing the normal force? So we still have same vertical load, but just increasing the normal force, see how much is the increase in the moment. Okay. And after increasing the normal force above the critical load, the result was negative 0.91 kilonewton meter, which was irrealistic because it is should be different value. There's too much difference. You see here it is 40. The moment was 3.44. When it is 80, it become only negative 0.91. So this value is not realistic. And now we want to discuss the result to see what is the problem with the result and how to avoid them in strand 7. Okay. If we look at the discussion of the result, when we apply the axial load of 0, the second order moment was 5.557 kilonewton meter, similar to the first order moment. Okay. But when the axial load increase, the second order moment becomes significantly greater than the first order moment. So when we keep increasing the normal force, the second order moment also increase. For n star equal to 40 kilonewton, which is close to n Euler or NOMB, the moment was 6 times greater than the first order moment. So if you look back here, when the normal force was 40 kilonewton, the moment was 3.44 kilonewton meter, which is about 6 times the first order moment. Okay, for n equal to 80 kilonewton, which is above the Euler buckling load in Euler, the computer or the software appears to have a given stupid prediction of the bending moment at the top side. So the prediction of the load of the moment after exceeding the buckling load was unrealistic or stupid prediction from the software. For the case we study, n equal to 30 kilonewton, the stress is is as in the strat initially considered. The second order moment of 1.56 is substantially larger than the moment of 0.914 kilonewton meter calculated by the first calculated on the basis of the first order analysis deflection. Okay, if we look here, how much is the moment? How much is the moment at case of 30 kilonewton? 1.56. This is from the software. But when we calculated, it was 0.914. So there is also still a gap between our second order or the manual hand calculation for the second order analysis and the load from the or the second order analysis from the software. This is because again this value, the 0.19, the 0.914 is based on this deflection. So because we based our calculation on this deflection, so this caused a difference in the result. Okay. Now we know that the second order analysis is significant, and we need to consider it in our design. And we know that also the software is not very exact to calculate the second order effect after the buckling load. And now we return back to the Australian standard to see the approximate amplification method. Okay, where is this approximate amplification method? If you go back to the Australian standard here, this file, the Australian standard give us the option to use first order elastic analysis with two methods. The first method is the moment amplification for a braced member. So we can use the method of moment amplification, which means that you're still using first order analysis, but with amplification of the moment. Okay, and this is where you can find it. So it is in under clause 4.4.2.2. Okay, so this is a braced element, and this is for a sway member. Okay. Anyway, if we return back to our calculation, so this is the approximate amplification method from the Australian standard. It is useful to consider the approximate moment amplification method of determining the second order moments defined in clause 4.4.2.2 of the Australian standard using this formula. The amplified moment is m star equal to delta B times mm star. So mm star is the first order moment. Delta B is amplification factor, which can be determined using this equation. Delta B equal to Cm over 1 minus n star over NOMB, and delta B should be greater than 1 because it is amplification factor, so it should be more than 1. M star is the approximate second order moment. MM star is the first order moment. Delta B is an amplification factor dependent primarily on N star and NOMB. As you can see, delta B depending on N star and NOMB. There is also a moment shape factor that's for approximate purposes may be conservatively taken as 1. As you know, there is two moment shapes. I will show you just quickly. Okay, so here we have delta B equal to Cm over 1 minus N star over NOMB should be greater than or equal to 1. Okay, so for if you read here, it was written in the slides that we have a moment shape factor. We have a moment shape factor which is called Bm because Cm here is given as Cm equal to 0.6 minus 0.4 beta m. You can find this in the Australian standard, the file you have, and this should be less than 1. So Cm is a factor equal to 0.6 minus 0.4 beta m. Okay, what is beta m? Beta m is the moment shape factor mentioned in the slides. Okay, beta m can be taken conservatively as 1, negative 1. Okay, in general, the standard mentions that beta m is the ratio of smaller bending moment to the larger bending moment applied to the element. As you can see, if we have element can have like M1, M2. So beta M will be, if we assume this is smaller, so it will be, and this is larger, so it will be M1 over M2. But sometimes, as you know, there is two types of bending. This bending can be like this. The two moments are in the reversed direction. So what happened to this? It will deflect in one direction. But for this type, if they are rotating in same direction, so what will happen to this? It will be two curvature. This is called one curvature. This is called two curvature. The standard mentions that beta m should be taken positive or negative. So positive when the member is bent in reverse direction, and the negative when it is bent in only one direction. So based on this two drawing, here it will be taken as negative, here it will be taken as positive. That's why for normal condition or for conservative solution, because most of the time this is our bending shape, so it will be taken as -1. Okay, so if you take beta m -1, So -1 times -4, it will be plus 0.4. So if it is 0.6 plus 0.4, so Cm is 1. So Cm equal to 1. This is also conservative. So based on the conservative assumption of beta m equal to 1. So beta m equal to 1, -1 lead to Cm equal to +1. Okay. Anyway, this is how to determine delta B based on Cm and N star and OMB. So I will go back to the share screen here. So this was written here, as you can see. Cm is 1 when beta m is -1. Okay, now if we go to the strand 7 results, as you can see, when if we use the strand 7 result, when n star equal to 30, the strand 7 give us the moment of 1.48. But when we apply the Euler load, it give 27.9, which is a realistic value. So this means that also there is a problem in calculating this value using strand 7. And here is a table to consider to see the difference between the amplification, to see the significance of using the amplification moment method and comparing it to the strand 7 results. So consider the following table that compares the approximate prediction amplification moment value to the exact result using strand 7. And here we have different applied normal force. Here is delta B, the amplification factor. Here is the first order moment, which is same value. This is the amplified moment, delta B M star, or we can call it M star. And this is M star from the second order analysis using strand 7. If you look here, so when the normal force is 0, delta is 1, so delta Bm is same. So, and also from strand 7 it is 0.58, so it is very close. The values are very close. If we apply only 10% of the Euler load, delta B will be 1.11, so M star will be 0.618. M star from the software is 621, so it is close again. 10, if we go 10, so we have 1.6 and 702 and 707 from software. So it's still close. Here 20, same. 0.75, 0.6, 9.6, 0.96, sorry. So it's still close. 30 kilonewton, 2.64. The amplified moment is 1.47. The software 1.485, so it's still realistic value. So this is the case of the original example. That's why there is a focus here. When the load is 40, we have delta B 5.82, the amplified moment 3.242, the moment from the software is 3.17, which is close, still close. If we apply the load, Euler load, delta B is infinity, because if you substitute here 1/1, it will be same value here, so they will omit each other, so it will be 1. 1 -1, it will be 0, so constant over 0 will be infinity. So the amplified moment is infinity, which means no solution. From the software, it is 27.93, which is also a realistic value. But we will see. We'll see if it is realistic or not. But if we go beyond the Euler load, 80, delta B is 1.52, -1.52. and the moment is negative 0.47, but from the strand 7 software it is negative 227, which is clearly incorrect result. Okay, if we discuss the result in this table as well, we will find that for n star 10% of the Euler load, the second order is not substantially different to the second order moment. When as n approaches the Euler load, the second order moment races away towards infinity. Okay, as you can see here, when you are close to the Euler load, the amplified moment reach infinity. There is a substantial agreement between the second order moments calculated using delta B and those from strand 7. Okay, this was clear. Up to here, it was very close. So from 0 to 40, it was close. And as the Serena standard states that delta B should be used when, yeah, so delta B can only used up to 1.4 because beyond this value, it is not accurate. Except, and so if you look back here, just go back again. Yeah. Okay, so this is a recommendation from the Australian standard to use delta B only up to 1.4. Okay, in this case, you can see it reach 5.8 and still close, but this just a special case for simple cases such as struts. So the case in this example is not the general case to use because the Australian standard has a recommendation to use only up to 1.4. Okay. For n greater than NOMB, delta B and the finite element method give incorrect and totally illogical answers. As you can see, both of the software and the Australian standard amplification method give unrealistic values. Okay, so this means that this solution is not valid for the loads above the Euler load. Okay, if we go back to the Strand 7 software, there is a solver named as linear buckling software. The linear buckling software or the linear buckling solver in the Strand 7 software calculates the loads, the failure loads for elastic buckling together with the mode shape expected for each of the different buckling modes. Okay, so the linear buckling calculates the failure load for the elastic buckling with the mode shapes. So this is how the software or what is the result expected from the linear buckling solver in the Strand 7 software. A linear buckling analysis is an eigenvalue problem which when solved produce eigenvalues and eigenvectors. So we expect from the buckling analysis an eigenvalue problem which give us eigenvalues and eigenvectors. The eigenvalue is a safety factor for the structure against buckling. So the values we got from the software is safety factor that can check if the structure is safe against the buckling or not. An eigenvalue less than 1 indicates that the structure will buckle under the influence of the applied load. So if the eigenvalue is less than 1, this means the structure will fail under buckling. And conversely, an eigenvalue greater than 1 indicates that the structure will not buckle. So if the eigenvalue is bigger than 1, this means that the structure is safe. And the eigenvalue is equal to the buckling load over over the applied load. So the buckling value, or sorry, the eigenvalue is the buckling load over the applied load. So if the buckling load is bigger than the applied load, this means the structure is safe. If the buckling load less than the applied load, this means that the structure is unsafe and will be subjected to buckling. Okay. And here is a screenshot from the Strand 7 software showing the linear buckling solver. After we model the structure on the Strand 7, we come to the solver and we select the linear buckling analysis solver. What we can see here is this box. This is the difference box in the buckling analysis. So we have initial conditions. This initial condition typically comes from the solution of a linear elastic analysis, linear static analysis. Okay, so the software is using the linear static analysis as an initial condition for the buckling analysis. This is what is mean here. If you want to change, so you need to tick this box and follow the instruction. The modes, the modes is the number of modes of buckling we expect for this beam, or the buckling number of modes we want to see for this beam. Okay, here for this example, it was taken as 4. So we are looking for four mode shapes. Shift, if the results reveal negative modes, a shift can be applied in the order to focus on modes which are of interest. So a shift means that if you see or if you notice like buckling mode that is not realistic or not required, so you can make a shift and go to the required mode shapes. Strum check is to find the exact number of eigenvalue with a particular range. Okay, so this is to find how much is the number of eigenvalues for this structure. Okay, so this is what we need to change if we are looking for a linear buckling analysis. So we can select the shape, shift, strum check, text or not text, and then we go to the linear static analysis. This is a screenshot from the Strand 7 software for our beam. Okay, and for n equal to negative 30 kilonewton. As you can see the result, just zooming. So here, the maximum deflection at mid-span is 0.0118, and the maximum moment is 0.557. So this is the linear static without buckling analysis. So this is the first order analysis. As you can see, the result is close to the manual result. So it's the same result regardless of loading change. Okay. This is the linear buckling analysis. So now we shift to the linear buckling analysis. So if you can see here, the solver, we take four modes for the solver. As you can see, we have mode 1, 2, 3, 4. So we have 4 modes. Okay. This one of the modes we have. If you can look at the first mode, how much is the value of the first mode? The value of the first mode is 1.609. So the predicted buckling load based on the first value, the eigenvalue is 1.609 times 30. So this is the first eigenvalue we have. And 1.6 is greater than 1 or less than 1? Greater than 1 means that the structure is safe under this load. The value of buckling load from this calculation will be 1.609, which is the value, the eigenvalue we got, times the applied load, which is 30 kilonewton. So the Euler load will be 48.27. If you compare to the, if we compared it to the manual calculation, how much was the load? Yeah, it was 48.3. So 48.2 and 48.3 is very close. So the values from the strand 7 linear buckling analysis for the Euler load was good. Okay, so if you can see here, this is a subdivision. Here is a note to, if you change the subdivision of the beam, maybe you get different result and compare the accuracy. So how much is the subdivision here? 1, 2, 3, 4, 5, 6, 7, 8. So the beam was subdivided to 8 parts or 8 sections. So you can subdivide to 10, 20, and so on, and see how much is the result change. Okay, so this is the linear buckling analysis from the Strand 7 software. This is some notes about the linear buckling solver of the Strand 7. The linear buckling solver can't find out the load needed to excite a structure instability unless the structure whose shape doesn't change as the critical load level is reached. So the linear buckling solver of Strand 7 can't find out the load that caused the buckling. So it cannot get you exactly what is the buckling load is. Okay, unless the structure shape doesn't change as the critical load is reached. Okay, so if the shape of the structure change before reaching the buckling load, the software will not be able to break the buckling load. This one of the first note we have. And it also cannot predict what happens to the structure when the critical loads is reached or exceeded. So the other comment on the strand 7 is that it cannot predict what happens after the buckling load. The linear buckling solver cannot be used to predict the actual displacement of a buckled structure. This can be studied by using a nonlinear static solver. So another comment or another problem with the linear buckling solver in strand 7 that it cannot study or predict the actual displacement of the buckled structure. And to know this, you need to use a different solver called nonlinear static solver. So there is still some drawbacks with the linear buckling solver. That's why we will need to use a different solver, which is a nonlinear static solver. Okay. Okay. Anyway, I think that's enough for today, and I will stop